Okay, in this video we're going to look at another system of linear differential equations with constant coefficients. So in other words, a system of differential equations of the following. So y1 prime is in terms of y1 and y2, and y2 prime is also in terms of y1 and y2, where a, b, c, d are constants. So we can write that in the following matrix form. So we have y1 vector prime is a matrix A times y vector, and previously we've shown that this has a solution. Y vector is e to the ta times some vector v, where this vector v is a vector of arbitrary constants. So that would be depending on the initial condition if we had one. So now in this video we want to look at this example. So we have y vector prime is 9 minus 5, 13 minus 7 times y vector. So we'll call this our matrix A. And that's equivalent to this system of differential equations. So we have y1 prime is 9y1 minus 5y2, and y2 prime is 13y1 minus 7y2. So since we need the matrix exponential to solve this, the first step of that is finding the eigenvectors and eigenvalues, which is going to depend on the characteristic polynomial. So we need to find PAX. So let's recall that's the determinant of xi minus a. So that's going to be the determinant of, let's see, x minus 9, 5 minus 13, and then x plus 7. Okay, good. So let's see what we get for that. So we're going to have x minus 9 times x plus 7, and then let's see, that's plus 5 times 13, which is 65. Okay, now we can multiply that out and we'll get the following. So this is going to be x squared minus 2x plus 63, minus 63 plus 65, but notice that's x squared minus 2x plus 2. Okay, so you could solve this with the quadratic formula if you wanted to, because we want to set this equal to 0 to find the eigenvalues. But I'll notice that this is pretty quickly turned into by completing the square as follows. So we have x squared minus 2x plus 1, like that, which means we can write this as x minus 1 quantity squared plus 1, which tells us that if we set this equal to 0 and solve for the eigenvalues, I get 1 plus minus I. So I've got complex conjugate eigenvalues, which means that my eigenvectors will also be complex conjugates. So let's go ahead and find those. So if we first take lambda 1 maybe to be 1 plus I, we need to find the null space of 1 plus I times the identity minus, minus our matrix A. So that's the same thing as plugging 1 plus I into this matrix for x. So let's see what we get for that. That's going to be the null space of, so we're going to have minus 8 plus I, so minus 8 plus I, and then 5, and then we'll have minus 13, and then we'll have 8 plus I. 8 plus I. Okay, good. Now from here, maybe a good strategy would be to multiply the second row by minus 8 plus I and see what happens. Or maybe, no, let's multiply the first row by 8 plus I. So we're going to do row 1 is going to turn into 8 plus I times row 1. So let's see, that's going to give us the null space of, so now if we multiply that out, notice we're going to get negative 64 and then minus I, so that's going to be negative 65, and then we'll have 5 times 8 plus I, and then down here we'll have negative 13 and we'll have 8 plus I. But that's really good because that shows that these first two rows are multiples of each other, and so we can cancel them, and so that's going to give us the null space of, let's bring this minus 13 up, and then we have 8 plus I here, and now we're going to have 0, 0. Okay, good. Notice if we multiply this by 5, we get this guy up here. So that's what we did there. Okay, now from here what we can see is that if we take x and y to be in this null space, you can solve for x and y after setting up a system of equations. And I'll skip that. It's fairly simple to do. And what you'll get is 8 plus I, 13. Okay. So actually, let's really quickly go over that. That's because we have negative 13x plus 8 plus I, y equals 0. And then we have y is a so-called free variable. Right? Okay, and then notice we can choose y to be 13, and we'll get that value for x up there. So I'll clean up the board, and then we'll jump to the end. But before I do that, I want to point out that since lambda 1 is 1 plus I, and lambda 2 will be 1 minus I, those, and we started with the real matrix, the eigenvector for 1 minus I will be the complex conjugate of the eigenvector for 1 plus I. So we don't even have to calculate that. So to summarize where we are, we have lambda 1, 2 is 1 plus minus I, so we've got complex conjugate eigenvalues. We've got complex conjugate eigenvectors, 8 plus minus I, 13. We can form this diagonalizing matrix P, which is 8 plus I, 13, 8 minus I, 13. I won't calculate its inverse. It's fairly elementary to calculate the inverse, but it's kind of nasty. And then we have our solution. Vector Y is this matrix exponential, e to the ta, and then c1, c2, where those are arbitrary, but that's going to be given by p. And then this matrix, notice that this is the same thing as e to the 1 plus I times t, so it's following the same nice form. And then down here we have 1 minus I times t. And then I should point out here we have this multiplied by this arbitrary vector over here. Okay, so now I won't show all of the details, but if we were to multiply that out, which is really just some multiplication of matrices, all of the complex numbers will cancel and we'll end up with the following. We can factor an e to the t out of the whole thing, and then we get cosine t plus 8 sine t. And then over here we have minus 5 sine t. Down here we have 13 sine t. And then finally over here we have cosine t minus 8 sine t. And that's going to be multiplied by our arbitrary vector c1, c2. Okay, so now if you want to write this as a system of equations like this, we could get e to the t, and now we have c1 cosine t plus 8 c1 minus 5 c2 sine t. And then down here we have e to the t, and then c2 cosine t plus 13c1 minus 8c2 sine t. Good. So that's what we would have for our solution in that form. Okay, that's the end of the video.